All right, welcome back. If you do trigonometry in upper level math, there's no avoiding this next topic that we're going to talk about today. We're going to talk about or introduce the unit circle. Now, the unit circle sounds pretty scary. It kind of is. That's why I refer to it as the unit circle of doom. But it actually allows us to get into doing a lot of trig or understanding a little bit more about trig. That opens up a whole field of study. Now, obviously, with only a few days left of school, we can't really get into some of the nitty-gritty of it, but we can at least begin. At least introduce it to you. So the unit circle, what is it? Well, the unit circle is a circle with a radius of 1, hence the term a unit circle, 1 unit. Now, the unit circle is positioned on the x and y axis as follows, where the center of the circle is 0, 0, and then obviously the circle is 1 distance away, all the way around 0, 0, hence the middle of the circle. And what we are going to do is we are going to take a look at a few angles as we go around 360 degrees around a circle. And we're going to stop at certain intervals. And we're going to fill a chart out that, again, is known as the unit circle. So let's go ahead and get started. So what does a unit circle look like? So what a unit circle is obviously it's that circle that I was talking about, 0, 0 in the middle. The radius of it as you go around it is 1. And what you'll notice is each of these sections represent an angle as you're kind of working your way around counterclockwise from 0 degrees all the way to 360 degrees all the way around. And what we're going to do is we're going to get started by filling in just the different angles. We're going to start with degrees, and then we're going to flip around and do radians now that we know that. And then last but not least, and this is where the trigonometry comes in, we're going to find some points on that circle as we go around the unit circle. So let's get started. We're going to start off with a situation that has 0 angle. So if you take a look at this right now, we're at 0 degrees. This first increment, kind of opening up from here to here, if we opened up, is 30 degrees. In fact, every chunk that looks like this, like that slice, is going to be going up by 30 degrees. So typically when I fill this out, I go 0, 30, I go to 60 degrees, I do another big chunk, I go to 90 degrees, because I hope you guys all agree that that is a nice right angle of 90 degrees, right? As we go a little bit further, 30 plus 90 is going to be 120 degrees. Whoops, put that in the wrong spot. We'll put that here. We will then go another 30 and get 150 degrees. We will go here, get 180 degrees, and then we will continue on as we rotate a full 360. So 30 plus 180 is going to be 210. 210 plus 30 is going to be 240. Plus another 30 and you get 270. Plus another 30 you get 300, and plus another 30 you get 330, and then plus another 30 you get 360. Now you'll notice that as I worked my way around, I skipped a few of these things. I skipped this potential one, I skipped this one, skipped that one, and that one. Now, the deal with these ones is it pretty much is the midway point as it looks in this image between 30 and 60. Another way to think about it is if this is 90 degrees, what would be half of 90 degrees? And the answer is 45. So halfway between 30 and 60 or halfway between 0 and 90 is 45 degrees. Another way to think about it is this angle is going to be 15 above the one before it. So 120 plus 15 is going to be 135. 135 happens to also be halfway between 120 and 150. This will be 225, because again, halfway between 210 and 240 would be 225. And then last but not least, between 300 and 330 would be 315. Now, let's talk radians for a second. Radians, as you remember, there's a few that are easy to remember. 0 degrees is 0 radians. But if you remember from last time, 30 degrees, each of these sections, again, bigger sections, is going up by 30 degrees as we rotate around that angle, as it's getting bigger and bigger. 30 degrees, if you all remember, is pi over 3, because 30 degrees, my bad, pi over 6. The reason being is 30 degrees is 1/6 of 180, and if you guys remember, 180 degrees is pi. So technically, what we are doing is each time we increase 30 degrees, we are increasing pi over 6. So as we go up in radians, we are going up 1/6 pi each time. So if you add another 1/6 pi to 1/6 pi, you would get 2 pi over 6, right? So again, you can think of it as pi over 6 plus pi over 6. You would get 2 pi over 6. Now the question is 2 pi over 6, that reduces 2/6, right? That reduces to what, pi over 3? So I'm going to write pi over 3 here. Now, if you take 2 pi over 6 and add another pi over 6 to it, you get 3 pi over 6. And 3 pi over 6, again, if you think about it, is going to be what? Pi over 2, right? Because 3/6 is 1/2. So that would be pi over 2. We'll add another pi over 6. So we got 3 pi over 6 plus another pi over 6 would be 4 pi over 6. And 4 pi over 6 reduces to 2 pi over 3, and so on and so forth. So we're going to add another pi over 6 to 4 pi over 6. We get 5 pi over 6. And then last but not least, we're going to add a pi over 6 to 5 pi over 6. We'll get 6 pi over 6. And 6 over 6 cancels, so you end up just getting pi. So hopefully you understand I'm just adding 1/6 each time to each one. And if I have to, I am reducing it to its reduced form. Then I'm going to add so right now this is 6 pi over 6. I'm going to add a pi over 6 to that as well. So that would be 7 pi over 6. I'm going to add another pi over 6. So that would be 8 pi over 6, and 8 pi over 6 reduces to, if you divided both of these by 2, 4 pi over 3. And then last but not least, 8 pi over 6, if I added another one, you get 9 pi over 6. 9 pi over 6 reduces to 3 pi over 2. And then if I add another pi over 6 to 9 pi, you get 10 pi over 6. 10 pi over 6 would be, what, 5 over 3, right? So it would be 5 pi over 3. And then we add another pi over 6, so that would be 11 pi over 6. And then last but not least, I add another pi over 6 to that, and I would get 12 pi over 6, and that reduces, if you reduce that fraction, to 2 pi, which would be 360. Okay, so that's one way people fill in this chart, is they just keep adding a pi over 6 and then reducing the fraction as they get there. Now, what to do with these ones? Now, as you remember, this is the halfway point between 0 and pi over 2. So what is half of pi over 2? And the answer is, if you were to do pi over 2 times a half, right, you would end up getting pi over 4. That would be the halfway point from 0 to pi over 2, and that would be 45 degrees in radian. So we're going to write pi over 4 here. So if you think about it, this is going up by a 1/6 of a slice each time. So 1/6, 2/6, 3/6, 4/6, 5/6, and then 6/6, right? These chunks are going up by quarters, right? And if you look at the chart, it does look like a quarter, right? So if you go from here to here, that's a quarter, a half. This would be 3/4, right? So this would be 3 pi over 4. And then on the flip side, if you think about it, decimals might make a little bit more sense, but if you flipped it to here, we are going up by quarters again. So this is 1 whole, right? If you add another quarter to it, you end up getting, what, 1 1/4. That fraction would be pretty much 5 pi over 4. So that's why that radian is the way it is. You go another quarter, you get 1.5 pi. And then you go the last quarter, and you would get 7 pi over 4. So that's why the radian here is 7 pi over 4. So now that I've kind of filled in all of this information, I've filled in all the angles, the next part of the unit circle is filling in these points. Now the points, some of them are easy, some of them not so much. So let's start with just this. If you remember, this is just 0, 0, right? If the radius of the unit circle is 1, what would this be point-wise on the x and y axis? If you guessed 1, 0, you'd be absolutely right. You'd be 1 away on the x-axis, but 0 up on the y. If you were to go, if this distance is 1 here on the y-axis, what would this point be? If you answered 0, 1, you are correct. And then if you go this way on the x-axis, 1 away from the 0, 0, it would make sense that this is -1, 0. And then last but not least, you can go ahead and fill in the last point that normally people will fill in, which is 1 below 0, 0. So again, 0, -1. So that brings us to these 3 points right here. And this is where the whole, trig part comes into play. So let me explain that. So if you take a look at just this section, I'm just looking at the first quadrant of my XY axis. The reason why this is trigonometric and why we care about this is the following. If I want to find this particular point, for instance, what I could do is I could imagine this as a hypotenuse of a right triangle. So if you imagine, I'm just having, this is my hypotenuse, this would be like the height of the triangle, this would be the distance. Now, it is possible, because this is opened up at 30 degrees, it would be possible to go ahead and solve that right triangle, right? I could solve for this length, and I could solve for this length. In fact, I could do that for all 3 of these situations, right? So on top of that, right, this 45-degree triangle would look something like that, where I could find the y and the x for that and get me my 2 points. Same is true for this particular triangle as well. So if I think of these like triangles, I can use the angle that my, again, rotation is opened up, and then I could help me get those 3 points. And using trig, I can go ahead and do that. So what I'm going to do is I'm going to quickly go over finding each of these answers. And you'll notice that what I did was I wrote the angle from the unit circle, but I also used the hypotenuse. I know that it's 1 because, again, it's a unit circle. So I know that this is just the distance from the center of the circle to that point on the edge of the circle. So let's go ahead and solve this. So let's start by solving for y. If I'm looking for y, I have my angle and I have my hypotenuse. This would be a, if you think of SOHCAHTOA, right? This would be my hypotenuse. This would be my opposite. And this would be my adjacent. So if I'm solving for y, I have my opposite here. I definitely know my hypotenuse, right? So opposite hypotenuse, that would be a sine problem. So I'm going to write sine of 30 equals opposite over hypotenuse, so y over 1. And then I would solve for y. So y is just going to equal whatever sine of 30 is. Now if you go onto your calculator, sine of 30, and I'll show you what I'm writing here. Sine of 30 is just going to be sine 30, boop, 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 is going to be straight up 0.5. So what we know is that the y value is equal to 1/2. So going back to my unit circle, I know that that distance here for 30 degrees is just strictly 1/2. Okay. Now let's get the x value of it. So in order to get that, I have an adjacent side and my hypotenuse, right? So it would be cosine this time, because it's adjacent and hypotenuse, of 30 degrees equals adjacent over hypotenuse, so x over 1 in this case. And solving for x, you end up getting x equals cosine of 30. Now, x, or cosine of 30, not so nice of a number. If you take a look at it, cosine of 30, you end up getting 0.866025, so on and so forth. Now, you could write that decimal there, and that would actually make sense, but if you remember, math people, we like to be a little bit more exact. Now, the exact number that is 0.866 is a square root number. In fact, it is going to be square root of 3 over 2. Square root of 3 over 2 is exactly that number. Now, there's some reason to it. I'm not going to completely go into it because, again, we have limited time here. But the square root of 3 over 2 is that. So what some people will say for this distance is instead of that 0.866, they'll just write square root of 3 over 2. Okay, so that would be the x value. So if you're filling this in, the unit circle, this would just be square root of 3 over 2. So the x coordinate of that point would be square root of 3, and the y would be 1/2. Let's find these other 2 points real quick. So for the 45 one, we're going to go ahead and start the same thing. Very similar process. This time it's going to be sine of 45 equals opposite over hypotenuse. So it would be y over 1. Sine of 45 times 1. So you would just cross multiply. Y would end up being sine of 45. Now, sine of 45 is this number, sine of 45, whoopsies. So sine of 45, we get 0.707. Again, into a decimal. The square rooted number that is equal to this is square root of 2. Divided by 2, you'll notice that it is equal to 0.707. So that is usually the exact number that people will leave for that y value. I'm also going to solve for this length. So cosine of 45 equals adjacent over hypotenuse. X equals cosine over 45. If you take, again, look at the calculator, we get cosine of 45. You end up getting 0.707 again, which is exactly what we got before. So x is going to equal square root of 2 over 2 as well. So filling that in, so far we got square root of 2 over 2, square root of 2 over 2 for this point. And then last but not least, we have that last triangle to deal with to get that information for the point up there. Same as before, we can use sine to help us solve for this y distance. So sine of 60 equals opposite over hypotenuse. 1 times sine of 60, y equals sine of 60. Sine of 60 is 0.866, and if you remember, that's that number that we got when we did cosine of 30. So really, sine of 60 actually ends up being that square root of 3 over 2 number. Next, let's do cosine of 60 equals adjacent over hypotenuse. So we got adjacent over hypotenuse. Solving for x, we get x equals cosine of 60. And when we do cosine of 60 on our calculator, we get 0.5. So again, it seems to be the inverted version of what happened at 30 degrees. So x equals 1/2. So let's go ahead and fill in that chart right here. So it would be square root, 1/2, and then square root of 3 over 2. Now, why this is important is this. If you know the information or the points for this particular quadrant, you will, because again, everything is symmetrical in the XY axis, you will be able to fill in all these other spots because these are pretty much the exact same points. The only difference would be is that X and Y will be either positive or negative depending on which quadrant of the circle you are in. So let me go ahead and fill the rest of this in on our original chart, and then I will explain what the whole purpose of the unit circle is in general. Like what does it help us do in terms of trigonometry? We can obviously see that trigonometry is involved with it, but how does that help us in trigonometric problems? So let's go ahead and fill in this chart now. So we've had all our angles, both degree and radian. We are going to go ahead and fill in everything we found out. So square root of 3 over 2, 1/2. We got square root of 2 over 2, square root of 2 over 2. We got 1/2 square root of 3 over 2. And if you look at it strictly over this way, you'll know that this one and this one are going to be the same. In terms of x and y. The only difference is on this side of the x-axis, after 0, 0, x's are negative, right? So I'm going to put a negative 1/2 there, but positive square root of 3 over 2. And if I look directly across from here to here, you'll note that these 2 points are the same as well. So square root of 2 over 2, square root of 2 over 2. But again, the x is negative in this quadrant. And last but not least, if you look directly across here, you get square root of 3 over 2 and 1/2, where the x is again negative, okay? Now, to fill in this one, what I normally do is I look straight down. So if you take a look here and here, these two coordinates would pretty much be reflections of each other. So this would also be root 3 over 2 and 1/2. The only difference would be is that in this part of the quadrant, both x and the y is negative. So I'm going to put a negative in front of both of these. This one, if you look straight down, would also be square root of 2 and square root of 2. But again, same idea, x and y would be negative. And last but not least, if you take a look at this point and you look straight down, you end up getting negative 1/2 and negative root 3 over 2 here. Now, on this side again, you could either directly look across from here, or you could look straight down from here. It doesn't really matter. So this point and this point are reflections of each other. So this would be square root of 3 over 2 and 1/2. This time positive x and a negative y, because again, where you're at in the xy axis. If you look straight down from here to here, this would be root 2 over 2, y negative. And then last but not least, we have 1/2 and negative root 3 over 2 for that last point. So if you take a look at it right now, we have a completed unit circle with kind of a quick explanation of where all of these things came from. Now, if you're wondering how this is useful and what this can be used for, I'm going to put it to you very, very quickly. This is used for quickly calculating trig ratios at certain degrees or angles or radians, right? So what I mean by that is this. Since each of these numbers came from either doing a cosine or a sine problem, if I were to say what is the sine of 30 degrees, well, I know that this 30-degree angle, right? I know that this length here, this y-coordinate came from a sine problem. So the sine of 30 degrees is 1/2. The way this works is that all of these y-coordinates on the unit circle are sine, I guess, ratios for each of the associated angles. So for instance, if I wanted to know what is the sine of 120, I could look at 120 and I could look at the y value at sine 120 and be assured that square root of 3 over 2 would be the correct answer to what is sine of 120. I could do this for radians as well. So for instance, if I wanted to know what is the sine of 4 pi over 3, I would just look at 4 pi over 3, the y value associated with that, and be assured that negative square root of 3 over 2 is in fact what sine of 4 pi over 3 is, right? So it can do both radians and it can do both degrees. Now, where did we get our x values from? If you remember, our x values all came from cosine problems, right? So very similarly, I could do cosine problems using this as well. So cosine of 60 degrees, you would just be able to find the location from whatever the angle is, and then look at the x coordinate, and that would tell you what cosine of 60 is. So 1/2. Same is true for this. If I wanted to know what is cosine of pi, cosine of pi would be, if you take a look at where pi is, the x value associated with that is -1. Or same is true as if I did cosine of 180. The answer would be -1. That's the x coordinate. If you don't believe me, I could, again, type this into a calculator in degree mode, and it would tell me -1. So what most people will put in their notes is that in the unit circle, the x-coordinate is the cosine for each angle, and the y-coordinate is the sine of each angle. Sorry for that really misspelled sign. And that is kind of like the very, very basics of what the unit circle is all about. So in your assignment today, you're going to be asked to fill out a unit circle on your own. Now, of course, you can Google unit circle, but it is important to start looking for where is all this stuff coming from, right? So hopefully that makes sense kind of where the degrees and the radians came from. And it also hopefully makes sense where these numbers came from as well. And then last but not least, the most important part is to understand that the x coordinates around the unit circle represents the cosines of each of the angles, and the y coordinates of each of the points around the unit circle represents the sine of each of the angles, okay? So go ahead and try the assignment. If you have any questions, office hours are daily, 1 to 2 p.m. You guys have a wonderful day. Talk to you later. Bye.